Hello, today's video is going to be a bit more ambitious than my last two. So basically there's this website called Pixel Art, and people can create pixel art and share it on here, and you can see all the different art. And they also have this weekly newsletter where they'll show you like the top art of that week, which is really cool, and I've been subscribed to that for a minute now. And I thought, as I was looking at those, I thought it would be cool to see those images kind of in person. And that's kind of what spawned the idea of this project, which is grabbing the pixel data from those images and displaying them locally on like an LED matrix. So that's the project, that's the gist of it, and get into that now. Okay, so the project is broken up into two main problems. One is I want to use a microcontroller for this, so what software do I need to get the microcontroller to get that image data and convert it into a usable format, also even connecting it to the internet in the first place. And two is the building of the LED matrix. I know someone might say I could have just used an OLED, and I could have just used an OLED, but the idea of this that sounded interesting to me was one pixel, like the LED would be a pixel in this, so I think it will be cool to build the display like that. So because I'm doing that, that's a whole other problem, like how do I build the circuit for that matrix. So that's the 2-1. Starting with the microcontroller. So the microcontroller I'm using is this ESP32 Vroom. I picked it up on Amazon for another project that I don't want to talk about. What a stylish PCB. What a stylish looking thing. Look at that. It's perfect. This was supposed to be small form factor too. This thing is huge. But anyway, so back to the project. I'm going to be running Python on this, and there's something called MicroPython, which is Python built for microcontrollers. So I'm going to run that on this because I figure it would be easier to try to do like HTML parsing and connecting to the internet with Python than it will be to try to do that in C. I've done the internet connection in C before, but that wasn't fun. So Python it will be. Also, lucky for me, I actually have a software engineer friend who said he was willing to write code for this. So that's taken off a lot of the work that I would have to do for this. So I can focus a bit more on the hardware, like building the matrix, as well as I told him I would figure out how to toggle GPIOs using MicroPython and set up that low-level code so that he could just call it in order to build the image. Okay, so with the software out of the way, I'm going to get into kind of how the hardware works for this, which I'll put up here now. Okay, so just starting with the outsides of it, what it is it's two 8-bit shift registers here and here. This one is for the columns and this one is for the rows. And the idea is an image, if you break it down into just pixels and assume the pixels are just on or off, it's just it's a 2D array. So what you can do is shift in the first row of data or the first columns of data into this top register. So if the first row of the image is 1011 1100, something like that, then you would load that information into this register up here, and you would turn on this first row on this shift register. That way, this current can sync only when row 1 is on. And that's important because, and this is, I haven't drawn this yet, this shift register will be connected to every single LED. There's not multiple registers for the different rows you have. So in reality, and this is a simplification, I'll show you what the actual circuit is. If you have here, this can branch off to an LED here, this can branch off, or let me do the same thing I did here. This can branch off to an LED here. So all these LEDs are, and keep in mind this is not the actual circuit, this is just simplification. All of these LEDs are in parallel to this column, to this first element of the column. So that's why you have this Darlington array on the side, because you can basically say, okay, turn on the first LED for this column, turn on the second LED of this column, etc. That way, when this is cycling really fast, you can turn this first shift register, you can put the information for one, which could be all ones, the next one could be all zeros, next one could be whatever, and you cycle through these faster than the human eye can register, so it looks like you're it's a full image, while in reality you're putting in a new value in the shift register per row and cycling through it. So that's why we have them in parallel, so we can have simplify the amount of registers we're using. So yeah, that's why they're in parallel. And so I also said this is a simplification of the circuit. So I'm going to show you one element now. So take, let's say, the first column entry and the first row entry. What it'll actually be is a resistor into a PNP BJT, which has its what is it? It's emitter and collector. Its emitter is connected to power, and its collector is then connected to an LED and another resistor to limit the current. I went a little past it, but this would then connect to the first element there. And to explain what it would look like in parallel, it would just kind of go past it and just duplicate that same circuit there. And so that's going through all of these elements. There's an LED like that, and then the next column has an identical circuit for all of its subcomponents. And that's the main circuit. And to explain kind of why I made the choices, one is the registers lets us remove the need to individually drive every LED with a GPIO or a buffer. For an 8x8 array, that's 64 LEDs. That's way more than the ESP32 has. And I'd rather not buy a microcontroller with a lot more GPIOs just to do that. And if you think about it too, if I want to go past 8x8, if I want to do 16x16 or 32x32, I think the calculation for 32x32 is over 1,000 LEDs. So it becomes unreasonable to try to directly drive every one. So that's why I'm using these registers to kind of handle that, to reduce the pressure on the GPIOs. Now for the BJTs, like why did I use a BJT and not directly drive each LED with the shift register? So shift registers, it depends on the kind you buy, but they're not really built to drive a lot of current. I'm sure there are some that exist that way, but your common shift register doesn't push a lot of current. It's more like 5 milliamps, something like that. And I want to drive every single LED with about 15 milliamps so they're bright. So directly driving with the shift register is not going to work in that case. So that's why I just use the shift register kind of as a control point, and I use a BJT to supply the current. I'm not going to go into too many details of how a BJT works, but just know that it amplifies the current here, so IB versus IC. I may have the direction of IC wrong. It doesn't matter too much. IC, when it's in saturation, I think I saw online, it's about 10x what IB is. So that's why I do it. So I can push with a little bit of current here, at let's say even 5 milliamps, and it would push 50 milliamps. It won't get to 50 milliamps because I'm not going to get too much into the details, but there's voltage biasing here. So as more current goes through here, the voltage drop across this resistor increases, and that will basically push the voltage here up to a certain limit, at which point the transistor stops amplifying and it finds that equilibrium point. So that's why I'm using the BJTs. And you may ask, why not use a MOSFET? And the thing is that we're using pretty low voltages here, about 5 volts, and I'm sure there are some PMOSs that exist that do that, but I figured it would just be easier to, because BJTs also come in the through-hole packages, and for MOSFETs, the through-hole packages, the ones with like actual leads on them, tend to be more power, so it requires a larger voltage, hence 5 volts won't work. So usually those ones with leads are like 10 gate to source, voltage, and I didn't want to deal with that. So the BJTs were simpler in this case. Now you also may ask why the Darlington array. Again, it's about a current thing, but the reason I use a Darlington and not just like another transistor or whatever is because each of these rows will connect to all of these LEDs going down into it. So if I want to drive a single row, this terminal here has to take 15 milliamps per LED, and there's 8 of them, so it's 15 times 8. Whatever that is, it's a lot. It's a lot of current. So, well, it is milliamps, but that is why I kind of use a Darlington, because the same thing, this shift register can only supply around 5 milliamps per pin, and if I just 10x that, like I did with the BJT, it could carry maybe at max 50 milliamps, but 15 times 8 is greater than 50. I don't know the exact number, but I know it's greater than 50. So by using a Darlington, I'll go into a little bit of detail. A Darlington is basically 2 BJTs fed into one another. So, or one of them feeds into the base of the other. So I know this with NPN, so I'm gonna draw it like that. Just see if I can remember this circuit. So what you basically do is you amplify the current through here. So IB here gets amplified here. So if this is, and we'll do IB1, or IC1, this then will get fed into another BJT over here. And this also has its high side over here. So basically what you can see is that I 10x IB1, again assuming the gain is 10, I 10x IB1, which then feeds into another base, which means that the current through here, which is IC2, and this is IB2, which is equal to this one. Anyways, IC2 is 100 times IB1 because IB2 is 10x of IB1, and we know that IC2 is 10x of IB2. So yeah, okay, I may not be drawing big enough, but the point is you can get a lot more current dumped through it when you use it in this format, and this is called like a Darlington. So by driving a Darlington rather than just a regular transistor, we can 10x this. So instead of 50, it's like 500 milliamps, which is enough for our case. So that's why I have a Darlington, and I also want to be able to scale this matrix into bigger matrices, or matrices. So right now it's 8 by 8, but if I wanted to make this 16 by 16, all I really have to do is just add another shift register, and I would have to add another Darlington and shift register here. The only issue is that once you start adding more columns, the Darlington here might not be able to handle the extra current, but that's for another point, and I think there's still a way to probably get around that. Maybe it's just another Darlington array or something where you put them in parallels, but anyways, I feel like I've talked enough on this, and that's the main gist. And for this first one, it's going to be 8 by 8, and for the next design, I think I might jump straight to 32 by 32, but I'm going to show those. So yeah, got lightheaded from all that talking. So yeah, that's the LED matrix. Hello, so this is going to be a test example for using these 8-bit registers. So I bought them and I put them on the breadboard. It also has the BJT section up here, the LEDs are down here, and I have buttons for the control signals of the register. So I'm actually going to walk through it now, just to show that it does work. So let's zoom in here. I am going to preemptively apologize because I don't think my camera distinguishes well the difference of LEDs. So I've got the data sheet up on my phone just so I can remember these pins. So right now, the output register has all ones, and it's ones because P and Ps are inverted. So if they were zeros, the LEDs would be on. So what I can do here is right now I have the serial line is tied up high, so when I press the button it goes low. So I can do that and then shift in to the shift register that value here. And now this middle button basically takes whatever's in the serial register and puts it on the output register. So if I press this middle button, we'll see one LED turns on at the top. And because the serial register is tied high, I can just toggle the clock signal to shift in basically nothing, but it will shift the whole value of the shift register. So we'll see the LED will move by 1. So if I just keep shifting and then sending it to the output, we'll just see this LED goes through the whole system. And similarly, if I were to just hold down the button here and then just shift in a value, I can, wait, hold on a second. I think I did something wrong here. I may have, okay, I jostled the resistor, which I think was for clear. So let me go ahead and fix this. So I'm going to set them all high now. And then I'm going to just shift in back a bunch of zeros. Okay, now I'll go ahead and hold the serial button high, send a clock signal in, and then send it to the output. And if I just repeatedly do this, we'll see that I actually keep shifting in a new value, so the whole array starts lighting up one at a time. This is the output enable here, so if I just press it, the whole thing turns on and off. Or it goes from whatever the value is to high impedance. So yeah, this is all working kind of as expected. And now, for the circuit, I have to say I did not include the Darlington. It's actually right here. It's doing nothing. Just because it's a bit easier to just wire these all to ground. So with that in mind, you'll see kind of that the grid is side by side. It's a bit it's hard to get a perfect 8x8 on a breadboard. So what I'm going to do next is take a proto board and actually solder in most of these components. And I think I'll also solder in the ICs as well, but I'm going to go ahead and just do that now. Okay, so I'm going to put together, just not soldering yet, but just putting it on a proto board, and then I'll solder that after that. So. Okay, I mean, take a look at that. That looks mesmerizing. Make sure I don't pull it over too much, because then the whole thing will come toppling out, but yeah. I think what I may do is solder this before moving forward, because this is, if I had to redo this, this would suck. So I might just go ahead and solder this now. Alright, there has to be a better way, because the edges alone were so difficult to solder. And also it's like, they got a little uneven. So I think what I'm going to do is flip it, land it, solder from there. Flip it, land it, solder from there. Man, that was tough. It's pretty jagged still, but just look how much, look how many leads there. All right. So I will need to decide what I'm gonna do next, but I may solder on the other side of the leads now, and then I'll go from there. So. Let's take a look. Yeah, it looks good. So I don't see any problems on it. I'll also be able to check a little later, but yeah, this looks good. Alright, so I did some mining off cam. I just went ahead, there's so much soldering that took place, I stopped recording and just went and finished it. So to give a little overview, we have the LED matrix here. I think I showed this earlier, but it's all soldered on the back. This feeds into the rows on this side. So the rows here is basically just a register in a Darlington array. And these are the control and power on here. And then on the other side is the columns. And here we have the register into the BJTs, resistors, all that. So now I can plug this stuff into the microcontroller, and in theory I can control it all. I haven't actually tested my software for controlling them, so that's kind of the next step. Is after this, now I can test the software. So that's where I'm heading next. Okay, so I got it connected to the ESP32 right now, and it is displaying this cool matrix effect. Unfortunately, this is not what I programmed it to do. It's supposed to have gaps in the middle, so I'm going to try to figure that out, but at least it's starting to do an interesting effect. And if I increase the frequency, it actually looks like the whole array is on, so at least it's kind of working now. Alright, so it's working now, so I'll show you how it works. So first you connect power to the microcontroller here, and then you give 5 volts. However, I'm using a USB converter. Now the system's powered, and I'm going to run a program with MicroPython that's going to display an animation I wrote in the matrix. Or not. Or it will do that. Not do that. So I just didn't have something plugged in. I didn't have the column drivers plugged in to the serial port. So now, if I were to do the same thing I just did. Okay, there we go. This is a little animation where it just goes from the outside to the inside. But yeah, I mean, now the only limitations for this is just whatever I can program for it. So I will say it is a bit of a pain to right now, in order to program this, I make a giant array. So I think in the future I'm going to figure out a better way to do this. Okay, so I'm going to end the video off there. The original goal of the project is still there. It's to get this image data from Pixelart as opposed to just an array for my own thing. But this video is taking longer than I thought I would, and I want to go ahead and just upload something. And I might do 2 parts, maybe 3 depending, because I want to still build a PCB for this, make it RGB, step up from 8 by 8 pixels to 32 by 32. It's funny, this project turned more into building a display than anything. I thought it was different, but that's basically what this is, minus the software. So, but I'm going to do that on the upcoming videos. I may have it in between while I wait for the PCB or something, but yeah, that's kind of where I'm going to take it now. So, thank you for watching.